So we were looking at the coefficients, the metric coefficients. G naught naught in particular looks like 1 minus 2 gm over c squared r, and we want to get a sense of the meaning, whether we need to consider values of the radial coordinates such that this thing is equal to 0. So that gives us an r equals 2 gm over c squared. And so we want to get a sense of this. And if we do this for, say, the Earth, where we use the mass of the Earth, then this r has a value which is 2 times g, so we have to pick a unit, 6.67 times 10 to the minus 11 if we're using kilograms, meters, seconds. The mass is about 6 times 10 to the 24 kilograms for the Earth. And we have the speed of light squared, so it's 3 times 10 to the 8 meters per second squared. And we'll get, let's make this 7. That's 7 times 2 is 14. This is 6. This is a 9, right? 3 squared is 9. And then we have 10 to the minus 11, 10 to the 24, and 10 to the 16. So 2 times 14 over 3 times 24 minus 11 minus 16. That's 26, 27, minus 3, right? So that's 10 to the minus 3. And so that gives us about, 8.5 times 10 to the minus 3 meters. And so the idea is we should consider this in case we have all the mass of the Earth within about 8.5 millimeters. So this is about a centimeter. So we would have to have all the mass of the Earth in here distributed spherically for this solution to be meaningful, for this r to become a problem for us we need to consider more seriously. So is this a worry? Should we worry about this? Well, maybe we can think about the density, right? What kind of density is this? Do we have densities like this in the universe? And that's the mass, 6 times 10 to the 24 kilograms, divided by the volume, which is 4/3. So 4/3 pi r cubed, 4 pi, so this is a 3 here. Let's do it like that. 4 pi radius cubed. The radius of the Earth, volume. Sorry, what am I talking about? I'm doing the radius of this, not the radius of the Earth. So we've put it into the space, so it's 8.5 times 10 to the minus 3. That's what I want to cube. I want to see what kind of density that is. Lost track of the plot here. So this is some roughly, I don't know, what is this? 6 times 3 over 4 pi, 4 times 3, that's about 12. 9 over, so this becomes a 2 pi, it's like a 6. 8.5 cubed, that's like 8 times 9 or something like that. So I don't know, times 6.5 times 10 to the 2. Here we have 10 to the 24, 10 to the minus 9 from there, and we get about 0.3 times 10 to the 31 kilograms per cubic meter. So what is that? That's 3 times 10 to the 30 kilograms. Okay, so what does that mean? Well, a neutron star has a density of 10 to the 17 kilograms. That's a pretty high density. We know about that. So maybe we don't have to worry about this. But we know of regions where the Schwarzschild radius is probably outside. In particular, I'm thinking of the center of our galaxy, where we have, where we can measure the mass given the motions of the objects, and we have a mass at the center there of about 10 to the 37 kilograms. It's well within an area that's, or a volume that's like the volume of the solar system. I think it's 0.08 astronomical units. So if that's the mass, then the Schwarzschild radius is 2gm over c squared. It's 2 times 6.67 times 10 to the minus 11 times that mass, 10 to the 37 over 9 times 10 to the 16. That's 14 here. 7 times 2 over 9. 10 to the 10 here, which is about 10 to the 10 meters. 10 to 10, that's about a tenth of the Earth-Sun distance. And so the density is mass divided by volume. That's 10 to the 37 over 4/3 pi times 10 to the 10 cubed, which is about, what do we have here? 2.5, 10 to the minus 1, 10 to the 37 over 10 to the 30. And that's, 2.5 times 10 to the 6 kilograms per cubic meter. That's definitely a lot less than the density of a neutron star. And this amount of mass in that region, it's in a region that's basically the volume of the region where the sun is in the solar system, the inner solar system. And we have 10 to the 37 kilograms, 10 to the 37 kilograms, 2 times 10 to the 30 kilograms for the sun. And that's about 5 million, 5 to the 6 suns packed in that region. And yet the density is much more reasonable density to expect. So maybe if you have enough mass in a region, you'll get a reasonable density and you can have a problem. So it looks like we need to figure out what is the significance of this radius.